Hey team, I'm Maddie. Welcome to Science Side Up, and this is episode 2 of Answers in Research Journal Club, where we sit down and we read a journal article that I really got to do journal article from the Answers Research Journal, um, and kind of read it and discuss it to some degree the way I would discuss a journal with my peers in my field. So in like amongst PhD students, a journal club is where you guys get together and you make it a point to read a journal article as opposed to a journal article or two. Usually it's like one or two a month. This is a little more frequent than that, hopefully. Um, and discuss it, and maybe sometimes that's like find issues with it or whatever have you, but it's a way of like staying current in the field. And I thought that was a nice relaxed way for us to do some video stuff together, some YouTube stuff together. Like I talked about in my last video, I've been dealing with a lot of burnout, but I have wanted to start doing YouTube stuff again, and this seemed like a nice easy way to do it. I am only like 2 months away from my PhD defense, and sometimes I just need a brain break, and so that's what this is. Have I fixed my microphone? Of course not. Do I still have code running in the background? Of course I do. Am I recording this the same day as episode 1 of this series? Yes, I just put on a cute sweater because earlier I left the house to go to the grocery store. Um, so that's where we're at. And yeah, thank you guys so much for joining. I'm glad to have you here. Hopefully, I'm in the live chat or the premiere chat or whatever. I know how YouTube works. Definitely do. Hmm. Okay, so the article that we are reading together um, is this heat problems with the Genesis flood Part 1, heat problems associated with Genesis flood models, Part 1, introduction and thermal boundary conditions. And like I said in the first part, um, we're reading this as though it's a review article, as opposed to an article that's like presenting an experiment that the author conducted. Because I think that's a little more, that gives us something closer to reality to compare it to. Um, I haven't looked up who the author is, and one of the reasons I'm not doing that is because I don't want to unintentionally engage in like a what's the fallacy where like this can't be true because of the authorship fallacy or something like that. That sounds right, right? That we like don't believe something because of the source, right? When in reality, like um, if someone says something true, then the truth value isn't dependent on who the person is, right? So we just want to read this, and I don't want to be biased against this person. Um, anyway, okay. So last time we read the abstract and the introduction, and today we're going to give a shot at this interior temperature and structure of the Earth. Um, One of the reasons I put Answers Research Journal in quotes there is because this is not a research journal. This paper is not written to a technical audience, right? When I present at a conference, which is in fact happening this Thursday, I've got a poster at the American Meteorological Society's big conference in the Polar Meteorology Symposium. Um, I am not presenting to I'm not even presenting to a general audience at the American Meteorological Society, right? I'm not even presenting to meteorologists, right? I am presenting specifically to meteorologists and atmospheric scientists who study polar weather, right? So it's a super focused audience of experts in the field, right? This is written um, really to a lay audience, and there's nothing wrong with that. So this really falls under the umbrella of science communication, not science research, right? Because this is just describing things, and he's saying things in here that you don't have to say to a specialized audience. And so this is like a geophysics paper. I am not a geophysicist. However, I guess other than in the sense that, like, atmospheric science sort of is an offshoot of geophysics. I have a general background in geophysics. My bachelor's degree, I double majored in math and earth, atmospheric, and planetary sciences, and I did mostly planetary science geophysics stuff as an undergrad. Excuse me, my nose is running for no good reason. Um, yeah. Okay. Um, and so I have a like I have a slightly above baseline level of knowledge of these sorts of things as compared to like the general population, but this certainly isn't my specialty. I certainly know more about geophysics generally than I do biology generally, right? I like to bring that one up because a lot of my YouTube science friends are biologists or paleontologists or anthropologists. And I'm like, cool, I know nothing about any of that. So this is more in my wheelhouse than those things. Sorry, I like to kind of state some of my credentials at the top of things so you guys have a reason to trust me at least a little bit. And my goal here is to kind of like look things up as we go. Um, what's my favorite part of this so far? My favorite part has to do with his acceptance of oxygen 18 isotopes for temperature stuff. I really hope we can get to that soon because we have a that record goes back like tens of millions of years. And I'm going to be interested to see what he has to say about that. Okay, so let's start with interior temperatures and structures of the Earth. Present day conditions within the Earth have been modeled using seismic, gravity, and geomagnetic data. Is this weird that that really should be gravitational? Like it's not gravity data, it's gravitational data. Um, Yeah, that's how I would say it at least. Okay. Geomagnetic data combined with compositional modeling of its constituent materials. That that's all true. If we want to know the interior conditions of the Earth, we do not have the ability to dig down and look at it. One of the oldest techniques used for studying this is seismic waves. The interior structure of the Earth are solid inner core, liquid outer core, mantle, crust. That was all determined in the like 1910s, maybe the 19 aughts. It was very early in the 20th century, just using seismometers, because it's really, really cool, actually, because there's two types of waves that come out of an earthquake: P waves and S waves. P for primary, but also pressure. So those waves go like this, kind of like moving a slinky, right? So it's this direction of compression, the direction that the material, in this case, the actual earth, is moved, is compressed and stretched, is the same as the direction of propagation. And then the other type of wave is the S wave, which stands for both secondary and shear. And those go up and down like a sine wave. But what's important here is that the direction that it oscillates is perpendicular to the direction of propagation. So, okay, so sorry if that sounded weird. I have no idea how that's going to sound on a mic. Okay, so um, key thing here is that those. Am I about to talk out my butt? Hold on, I'm googling myself before I accidentally say something wrong. Um, yeah, yeah, yeah. Ha. Okay, I was gonna say it right, but I'm glad I checked myself. So P waves travel through both solids and liquids, but S waves can only move through solids. So, if an earthquake happens here on the opposite side of the Earth, um, those S waves don't get all the way through, whereas P waves do. So you can, with a sensitive enough seismometer, and seismometers are pretty darn sensitive, you can measure, make an Earth sandwich with your like earthquake seismometer. You can measure P waves at the your bottom piece of bread of your Earth sandwich. You won't measure S waves. And then you can kind of track that out. Okay, here, 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 and here, I get P waves, but not S waves, right? And then, ooh, I get to this point, and over here I have both P waves and S waves. So that we have this shadow of where there are no S waves. You can use that to measure out the size of that inner liquid core. Sorry, the outer liquid core. You can do that. And then by that exact same process, except slightly more complex using uh, wave reflections, you can map out the rest of the Earth's interior. So same idea, but it gets a little more complicated. So that's what's going on. That's what. So that is the oldest way we have of measuring the interior structure of the Earth. Gravitational data. Yeah, so you can use that to think about if there was a lot of mass over here, but not as much over here, right? That would make a measurable gravitational distortion that we could measure. A measurable distortion we could measure. Yes, yes, absolutely. That's what I meant to say. That, that's why these are unscripted. um, and then geomagnetic data. So that's going to have to do geomagnetic data. What does that tell us about the interior structure? I'm guessing that's going to tell us something about, so like the Earth's magnetic field is basically generated by the convecting mantle. Um, and so I guess measurements in the I'm trying to figure out what this means as we're here. So I guess what that's saying is that like information we can get about the magnetic field here at the surface tells us something about the interior structure. Because like, why would you have a stronger magnetic field here versus here? What does that tell you about what's happening internally? That all makes sense. That's not my field, but that sounds like something you could study real intensely for a career, right? So that's cool. Would fully love to see a citation here, right? No citation. So how am I supposed to look up what this is, right? This is supposed to be a science paper. There's no trust me bros in here. Um, compositional models are informed by comparison. Compositional models. Okay, so that's like what is the Earth made of? And how is that different in the different layers? We talked a little bit about that last time. Compositional models are informed by comparison with other bodies in the solar system. The sun, not super the sun. We don't, but definitely meteorites and other planets. Yeah, so that's sorry. This is a fun sentence, and I would love to see a citation for the sun. Um, so God, sorry, I need to take a sip of my afternoon coffee here. Um, so one, other than the moon, we've never done a return sample mission from anywhere, right? So this other planets, right? That really means meteorites because like we only know the only rocks from Mars we have are Martian meteorites that have landed here on Earth. Um, uh, I don't know what the composition of the sun would tell us about the composition of the planets. That has to do so like the reason I'm baffled by that has to do with like the solar disk theory for solar system formation. Um uh I'm not sure if that's the actual name for the theory, but it's like where you start with a protoplanetary disk of like dust that then and it's all in a gas form and then it condenses out and what elements condense out is a function of temperature and therefore distance from the sun. And when you do that, you track like the rocky materials of the inner planets, the gaseous materials of Jupiter and Saturn, and then the icy materials like methane ice and stuff like that of like Neptune and Uranus, and that it kind of all tracks out in a very general way. Um, I have a textbook that talks about this, but it's not right next to me. Let me see for a minute if I can't find there's a graph I'm thinking of. So let me see. Um Protoplanetary disk, element condensation. Protoplanetary disk, dust condenses gases in the protoplanetary disk. Okay, NSF, do you have a plot I want to use? I'll switch you guys over to my Hail Mary Google search. Let's see what we can find. And present, share screen. I would love to share this one. Excuse me for the infinite thing for a second. Here we go. Right. Okay. Yeah. Oh no, this is an NSF award. That's not what we want. Maybe let me jump to images, not videos, images. do 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 do. This isn't the exact one I was thinking of, but that should be pretty close. Yeah. Okay. Cool. So here we go. This is pretty good. Condensation of the solar system. So this literally means condensation in the way you're thinking of with like water, right? Because this is everything is a gas and then it has to condense to its like solid state. And so this is temperature, right? Which you can think of as proportionate to distance from the sun. And then this is going to be total pressure. Amazing. And so at these hot temperatures that are close to the sun, right, we get, oh, look, minerals, right? So you don't need to know geology to think about this, right? But hey, look, this is like hibonite plus perovskite and graphite and Ca1. That's like calcium. That might be like calcium aluminum inclusions. I'm not sure. But notice when it's hottest, the first things you get, so the things that you're going to get closest to the sun, are rocks, right? You're getting these different, again, mostly rocks, and there's definitely some metal. I'm not sure what this dashed pink and black lines. Oh, look, feldspar, right? So like we've got feldspars here on planet Earth. We've definitely got olivine. I know the moon has a bunch of olivine. And then as we get out here, this is like titanium trioxide, right? So we're getting to different elements, different things that are gonna like uh precipitate out at colder and colder temperatures. I'm wondering if there is this one doesn't go as far out as I was hoping because like you get olivine at Earth and the moon. But if like this chart continued out, like down here is where you get your like ices that are on like Neptune. But anyway, so yeah. Let me stop sharing so we don't get the infinite windows. Presenting, and we'll go back to the article. Bam. Okay, allow. I'm gonna check my code real fast, make sure it's still running happily. Oh, it still is. Beautiful, beautiful, beautiful. Okay. So yeah, so that's where we get some of our composition models. By the way, like with the moon rocks that we have, one thing that's really cool about them is that the composition of the moon seems to exactly match not Earth's composition as a whole, but specifically the composition of the Earth's mantle, which is really cool. So that's where we get the idea that this like a Mars-sized body early in Earth's history slammed into like the molten Earth and ripped off a bunch of its mantle material and formed the moon, um, which is very cool. Okay. But so yeah, so we actually know a decent amount about the composition of planets and things like that. So we have a very good sense of what total elements should be making up the Earth, right? That is like that science that's pretty old, right? That's pretty well established. Anyway, a representative model is the preliminary reference Earth model of Dzwonski and Anderson, 1981. The data of interest here is conveniently summarized by Stacy and Davis, 2008, lists mechanical properties and thermal properties. Okay, cool. So let's look up what is that? I'm gonna be shocked if this thing has a bibliography. So, but I want to find Dzwonski and Anderson 1981. Please have a bibliography at the end. Oh my gosh, we have a bibliography. Okay. This is everything he said, but he doesn't. Okay, I'm gonna calm down. This is a huge bibliography, and I've seen like 3 citations. Um, D. Okay, here we go. And Anderson 1981. Physics of Earth and Planetary Interiors. Okay, great. That sounds like a real journal. I'm sure that's a real paper. Let's go take a look at it. Let's take a quick look. Preliminary Reference Earth Model. So I'm going to pop over to Google Scholar is what we'll do. I want to do that one. Go here. So let's just go scholar.google.com. Earth model. Oh, yeah. Look at that. Cited by over 11,000 people. That is, the number of citations is roughly proportionate to the importance of the paper, right? So this paper cited by 3, probably not very important. When was this one published? 2020. Yeah. Okay. So this looks like a very established paper. Okay, amazing. We won't read it. But I am happy to see our author here actually citing a relevant paper in a real journal. That makes me so happy. Okay, here's where we are. Okay, the resulting global averages as functions of distance from the center of the Earth are shown in figure 1. Okay, so let's look at figure 1. Earth's, okay, cool. So this is from that other source. So this is not from the source we just looked at, but from the one that summarizes it. So that's nice. We're just gonna kind of trust this. We have no reason not to. So this is, let's see, Earth's globally average internal pressures in black against this y-axis and temperatures red this y-axis as functions of radius. So this would be 0 would be the center of the Earth, and then here is the Earth's crust. Okay. And so things to note are going to be that jump. That's going to be a big deal. And I'm guessing that this is related to the compositional jump. So we're going from iron nickel to boop, not iron nickel, to silicate material. And then, yeah, pressure has a nice, do you notice it's kind of making an S curve, right? So it's a very lazy looking S. That, and it's showing the like transition of the S right around that same point. That tells us that's like an inflection point. And so that's all making sense to me. These feel like we're seeing a transition in temperature and pressure related to a change in material, right? And then we could know things about material properties, right? We could go into a lab, test material properties at these temperatures and pressures, what materials exist at these temperatures and pressures, right? That's fun. Okay, cool. The CMB, core mantle boundary, okay, cool, shows its presence by a jump in temperature and a bend in the pressure profile, which is what we just noticed, cool, indicating a jump in density at a depth of about, this 2,891 kilometers if we're going from the top down, or 3,480 kilometers if you're going from the center out. Thermal boundary layers are evident on 1, at that boundary, and 2, at the upper mantle between the transition zone whose upper boundary is at a depth of 410 kilometers. Here's a paper to look at. So that transition zone, that's where we go from like the mantle to the crust. And absolutely. So here and here, we see these jumps in temperature, discontinuities, if you will. One of the things that's going to do is like transport. The first thing I think of is that transport of material and even energy across that boundary is probably going to be pretty hard. Um, we've made pretty clear zones. That's a pretty firm boundary, and getting through natural processes, material and energy, any type of transport across that boundary is it's just going to be difficult. You're going to need something interesting to be going on. This is sort of like, okay, in the atmosphere, we go like surface of the earth through the troposphere. And then there is this like point where temperature is just constant. And then it starts to warm with height instead of cool with height. And that part where it's constant is called the tropopause. And it separates the troposphere from the stratosphere. And it's actually very, very difficult. So if you've ever seen like a big thundercloud, the reason it has a flat top, or even the top of a hurricane, the reason those guys have flat tops is because that air rises until it hits the troposphere, excuse me, the tropopause, and then it can't go any further up, right? It has this boundary. And so it goes and circles back down we get these convecting cells coming back down to planet Earth. And really, really, really strong, like thunderstorms with a strong hail core can punch through that boundary, but it doesn't go very far. So where you have these like sharp distinctions in material properties, like those make physical real boundaries. And what we're seeing is this sudden drop in pressure and drop in temperature. But specifically a very sudden drop in temperature. And same thing here. So if we're thinking about, yeah, transporting things from up to down is going to be effectively impossible. Because if I'm trying to move stuff this way, I'm not going to get past that boundary, right? Basically, like uh, to get heat from here, physically from here to here, this has to warm up to this hot, right? I have to warm up by 2000 degrees Kelvin to move from here to here. And so it's just going to be very hard. I hope that makes sense. Okay. Um, Okay, so we talked about we see these boundaries and what that might mean. Such boundary layers are expected in the presence of the mantle convection associated with plate tectonic motion because there can be no advective heat transport through the core mantle boundary or through the lithosphere except at MORs. That's like mantle something something and other localized volcanic outlets. Has he defined MOR? Sure doesn't. Fun. Previous. MORS. Let's try that. Okay. Yeah, that's the first time. So cool. That's fun. I love it. Listen, you always define terms. You always define acronyms in a paper, even if it's to your audience, but especially if it's to a more general audience. Gosh. Um, um, yeah, but that's referring to like volcanic activity where mantle material comes up to the crust. Okay. So advective, if that's an unfamiliar term, to advect is to physically move something from one point to another. So temperature advection is like, hey, my coffee is hot and I moved this hot thing over here. Therefore, I advected warm temperatures over here because I physically moved something hot from point A to point B. So this is saying that that advective heat transport, right, is real hard, except when you have a volcano, right? So we're not going to get, say, heat energy out of the mantle. We're not going to get heat energy out of the mantle to the crust by moving the material unless it's a volcano. Um, okay. The temperature drop through the region above the transition zone is approximately 1600 Kelvin. The larger part of this occurs across the lithosphere. Lithosphere should just be that's like the crust and the mantle, right? What is the lithosphere? Sorry, like I've heard of that. Excuse me. Okay, the lithosphere is the crust and like the top of the mantle. I knew that was a thing. Okay, lithosphere, the crust and the top of the mantle. Okay. The larger part of this occurs across the lithosphere, where also the temperature gradient is steepest. The thickest the lithosphere, although very variable, is typically of order 100 kilometers. So, okay, we've got a citation. We love to see it. Um, so this drop, what they're saying is that this change in temperature of 1600 Kelvin is happening in 100 kilometers. So um, relative to the size of the Earth, that's a huge temperature change in a short distance. Okay, cool. Given spherically symmetric models of the kind proposed by that Dzwonsky and Anderson, 1981, as a reference, geophysical evidence, mainly seismic, reveals considerable mantle heterogeneity. Okay. Heterogeneity. Okay, so what this means is what they're saying is that if I scoop up a piece of mantle from under Australia and then I scoop up a piece of mantle from, I don't know, the middle of the Atlantic Ocean, both of those pieces of mantle should be like compositionally the same. They're made of the same stuff. So we think of it as ice cream, right? Neapolitan ice cream is not heterogeneous. That would be if I took a scoop from over here, I got vanilla. I took a scoop from over here, I get chocolate. But if we stirred that monstrosity together for a chocolate, strawberry, vanilla, fully mixed together, I guess that might taste like vanilla chocolate covered strawberries. We have to mix all of that together so that no matter where I scoop from, I'm getting the same total composition. Hope that makes sense. Okay, the heterogeneity is especially pronounced in the D double prime region, the lowest 2 to 300 kilometers immediately above the core mantle boundary, which is characterized seismically by a decreasing gradient of both pressure wave and S wave, P wave and S wave velocities with depth. Okay, the heterogeneity is understood to be in temperature, composition, and material phase. Okay, so when we say heterogeneity, we don't just mean composition. We also mean my ice cream is the same temperature throughout, none of this melting on top and more frozen on the bottom, right? For this thin layer, the temperature is the same everywhere. The composition is the same everywhere. Um, and the material phase, right? So it's an all solid, there's no liquid. Uh, yeah, yeah. In my ice cream example. Cool. Regions of increased P and S wave speeds generally signify descending slabs interpreted as subducted material, while lower wave speeds signify upwelling or mantle plumes. So yeah, this is that size. Is it seismography as a field is very cool. The people who study that are very, very clever. And so if we have like, say, where you have like the oceanic plate that's slipping under the Asian plate, the Asian continental plate, like right where Japan is, we could see the subducting, this is the subducting plate. We could see that subducting oceanic plate under the continental plate that makes a characteristic pattern in our seismic waves. That's all this is saying. This is kind of saying how we know things. So I actually like I don't have any problems with this so far because he's just referencing real science, right? And he's actually citing stuff, which is very nice. Excuse me, goodness. Okay. In many cases, subductive material has apparently been flattened in the transition region around 660 kilometers below the surface. There's a citation for that. However, of the Farallon slab under North and Central America and the Indian Tethys slab under the Himalayas and Bay of Bengal, subduction has reached the lower mantle. Bob Gardner, 2003, cites as evidence of mantle heterogeneity, one, a ring of dense material at the bottom of the mantle lying roughly below the perimeter of today's Pacific Ocean, two, super swells in the South Pacific and under the East African Rift Valley, regions of locally elevated surface caused by rising mantle plumes. Hey, Vanderhulst. I think I know him. Um, Maybe. Let's see. Because I think that's Rob Vanderhulst. He took over as president. If it's who I thinking of, then he took over as president of the Earth, Atmospheric and Planetary Sciences Department my senior year of undergrad. Vanderhulst. Next. Yeah, Rob Vanderhulst. Yeah. Cool. Okay. Okay, Adobe, that's fine. Okay. Baumgartner. Again, so I don't want to fall into that, like, whatever it's called, the author fallacy. Like, I don't want to trust that just because I know him to be a good scientist. And so that's not in and of itself a reason to just trust the results, right? Like, we should always question things. But the trust I'm getting here is that, oh, okay, he's a legit science, is the, like, I know any paper he published underwent serious, strenuous peer review, right? Like, that's a thing that I know to be true. Um, and so, uh, yeah, that's kind of what I'm trusting there because as I hope one of the things we're seeing as we're reading through the Answers Research Journal is that these don't undergo like rigorous peer review. These types of articles could never get published in a like non-creationist journal, not because of like not innately because of the ideas they're proposing, but because of the like frankly the sloppy manner in which they are written, right? And again, this is written to a lay audience, not to scientific peers, right? So far this part is a pretty good review, of this stuff. Like this would pass muster. This section we're reading right now would pass muster for the introduction for the introduction section of a paper or as a component of a review article, right? But so far, no science has been done, right? And in the introduction, we saw some claims being made without citation, which would be a no-go. Anyway. Okay. Density homogeneities up to 3 to 4% level, assuming this to be entirely thermal in origin. He infers temperature differences of up to 3 to 4,000 Kelvin in the underlying mantle. He argues that differences this large are unlikely to have persisted for 100 million years, as in the uniformitarian chronology. I doubt they use that phrase uniformitarian. So, but are perfectly plausible if the subduction occurred only a few thousand years ago. Okay, this is Baumgartner cites density homogeneities up to 3.4. Okay. However, Baumgartner does not attempt to justify his assumption that compositional and phase-related contributions to density can be ignored. I'm having trouble understanding this sentence because Baumgartner, I think that's a Baumgartner. Here we go. Baumgartner, it was like, what was the next? 2003. Okay, so here we go. Lots of Baumgartner. Um, Baumgartner 2000, 2003. Yeah, catastrophic plate tectonics, the physics behind the Genesis flood. Um, so that's not a paper that I trust, right? And actually, because like I know it wasn't properly peer reviewed, because it's in. Actually, let's take a look. Catastrophic plate tectonics, the physics behind the Genesis flood, and the proceedings of the Fifth International. Blah 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 blah. So let's take a look. Share screen. That no, not that button. I want to do this button and allow and do this and do this. Can I find this paper? Okay, maybe this should be our next journal club paper. Okay, catastrophic plate tectonics, the physics behind the Genesis flood. Okay, is this brilliant? This is the whole paper. Okay, so okay, you know what? For now, what we'll do, I'm going to. Can I please download? Um, Maybe I'm downloading it right now. Sure. I'm saving it right this second. You guys just watched me do that. And we will read that in the future. So, right now, what we're going to take into account is just that um, he is citing this thing. Okay. So, we're going to do this. Okay. So, no, next, because I'm going to get us back to where we were. Okay. Okay. Here we go. So, we just talked about the like density differences in material in the mantle, and then he's saying that like that's accepted in like the general science, and then here we're going to say Baumgartner in this paper that's explaining catastrophic plate tectonics um is going to say that uh mhm, basically that these density homogeneities um are unlikely. They He's going to say they can't be old, right? So we'll just accept that that's like an argument that is put forth, and in the future we will read that actual paper, right, as part of journal club. Okay. However, Baumgartner. Okay, cool. So let's jump to the next paragraph. Mantle heterogeneities, especially where they relate to subducted material, thus serve as an archive of Earth's tectonic history. I think I can agree with that. That sounds right. For example, a recent study has revealed in uniformitarian. See, I don't like that phrase, that uniformitarian terms, because like nothing in modern science says uniformitarianism is a thing. In fact, the first time that is a term that I, a like professional discount scientist, at least for 2 more months, I'm a discount scientist. Um, have never heard that term uniformitarianism used in anywhere but creationism circles. So, because it's like it's very old and outdated. And so if that's the idea that everything happens gradually, uh, and like everything happens slowly, gradually over time, which basically like sure, unless you have evidence to the contrary, right? Like, don't assume big catastrophes unless you have evidence of them, is sort of the modern understanding of uniformitarianism. But again, the only people that use these terms are young Earth creationists, in modern times at least. Okay, a link between the flux. Okay, so in this is, but I think what he's trying to say here is like in non creationist terms, a link that there's revealed a link between the flux of subducted material reaching the core mantle boundary. Okay, so flux is transport of stuff across an area, right? So if we've got a plate, we're bringing material from the crust into the mantle. And then if that gets all the way down to that mantle core boundary, that is going to happen, right? Eventually, because the mantle is circulating. the mantle is convecting. So when we have a plate, a subducting plate diving under the mantle, this material is going to travel all the way through the mantle if you wait long enough, right? But we're talking about tens to hundreds of thousands of years. Um, okay. So a link between the flux of subducted material, so that material getting down to that core mantle boundary, and the timing of geomagnetic field reversals. Well, that's cool. I would actually like to read that paper. Geomagnetic field reversals. So the Earth's magnetic field sometimes just shuts off and reappears upside down, and we actually don't know why. Um, yeah, we don't know why it weakens, we don't know why it shuts off, we don't know why it reappears upside down, but we do know that it does that. And that currently the Earth's magnetic field is weakening. So sometime in the next like 14, between tomorrow and 14,000 years from now, the magnetic field will shut off. um, anyway, so this sounds like one proposed mechanism for that. To my knowledge, that's still an open question, but I might need to revisit it. Hold on, team, I'm checking my code. Okay. Sweet. It finished running. So I'm going to keep talking to you guys to the end of this section, and then I'm going to go finish up my dissertation work for today, and then I'm going to go play with my baby. She's like a toddler now, though. She's so big. Okay. Okay. Mantle heterogeneities and the structures they represent should therefore be taken into account in the development of coherent, fully integrated flood models. Okay, sure. Let's take into account real science when we're trying to propose a new theory. That's how I'll phrase it. Baumgartner 2003, that's that what is catastrophic plate tectonics thing, has considered them qualitatively in this light. However, a detailed assessment of the significance of mantle heterogeneities in the context of flood heat and flood modeling are more generally is beyond the intended scope of this article. Such an exercise should be undertaken in due course. So that kind of cracks me up. And you know, like I can't fault him because I definitely am trying to sneak a line in my dissertation. That's like this explanation is presented as a possibility, not a conclusion, and fully investigating it is beyond the scope of this work, right? Um, so, can't that's what it's saying. It's that, like, this taking into account these mantle heterogeneities and the terms for, like, the heat fluxes that you would get if there had been a global flood, um, as young Earth creationists believe it occurred. That's definitely something that should be taken into account, but, you know, I'm not gonna give give them flack for that, not really, because, again, this reads like a review article. It's just kind of presenting all the available information. Um, okay, cool. So we've been going for 48 minutes and we just got to the end of a section. So ocean temperatures, I think is what we'll read next time. Which will be very fun. Who knows? Maybe I'll get that to that again later today. But right now, my code finished running. I got to go check on it. Send some figures over to my advisor to update a paper that we're also working on while I'm writing my dissertation and presenting at a conference and probably writing a oh shoot, I've got to write an abstract for another conference and write a proposal for postdoc funding. So that's my life, and you guys are really cool, though. Thank you so much for hanging out. I hope I'm in a live chat chatting with everybody during a premiere. I genuinely hope you're doing well, and I genuinely appreciate everybody coming to hang out. I hope these can be semi-regular things. I would love to get back to doing live streams, but through so this the 30th of January, 2024. I'm graduating, and so between now graduation and then starting my postdoc in June, um, I'm gonna alternate wildly between being just a stressed panda and overworked and needing to hang out with internet friends. So I promise no consistency, but I'm gonna do my best to see you guys more. So have a great day. Like I said, I'm gonna go finish up work and play with a toddler. So I'll see you guys next time. Okay. Bye, team.